For this example, we want to solve the initial value problem 2y prime minus ty equals 1 with y of 1 equals 4. Again, we must put this in standard form before we try to solve it. So we divide through by a 2 to get we want y prime minus t over 2y equals 1/2, the same initial condition. And now we come for integrating factors. So we have that our function p of t, our coefficient, is negative t over 2. Its antiderivative, big P of t, is then negative t squared over 4, since it's just a polynomial. And so our integrating factor, mu of t, is going to be e to the negative t squared over 4. Great, let's multiply both sides by the integrating factor and see where that gets us. So we end up with an e to the minus t squared over 4 times y prime minus t over 2 e to the minus t squared over 4 y equals 1/2 e to the minus t squared over 4. This side is, as expected, e to the minus t squared over 4 y prime. So now we just integrate both sides. And on the left, we're going to get e to the minus t squared over 4 times y. And on the right, we're not so happy. So on the right, we're going to see 1/2 the integral of e to the minus t squared over 4 dt. And that makes me unhappy. Why is that? You might recognize this as one of the integrals that we know we cannot evaluate explicitly using normal techniques, or really at all. That is an integral that is not expressible in terms of simple functions, so we can't actually write out a formula here. If you've taken a stats class, this is representative of the bell curve, or the normal distribution for things, but we don't have an actual formula for its integral. So what can we do? Well, we're going to end up leaving our answer here as an integral. One way we can make this look a little bit neater is in making this a definite integral instead of an indefinite integral. So what I'm going to do for that is I'm then going to rewrite this now as 1/2 integral of e to the minus, I'm going to use s as sort of my extra variable here, s squared over 4 ds, and I want to put a t here as the upper bound of the integral. And I can pick whatever I want now for a lower bound, and to make my life easier, I'm going to pick this value, the value where I have my t initial condition. And we'll see why in a moment. So I put a 1 down here. And now I can, as normal, solve for y. So y of t will be 1/2 e to the t squared over 4, because I'm multiplying both sides by e to the t squared over 4, times the integral from 1 up to t of e to the minus s squared over 4 ds, and then plus c times e to the t squared over 4. And that works for a general solution. It still involves an integral, but it is an explicit form solution for this problem. Now, why did I write it in that particular form? Let's now try to meet the initial condition here. So for the initial condition, I want y of 1 to equal 4. So let's plug in 1 and see what happens. Y of 1 equals 1/2 e to the 1 squared over 4, integral from 1 to 1 of e to the minus s squared over 4 ds, plus c e to the 1 squared over 4. Now we notice right here, because I picked 1, the value that I have for initial condition as the lower limit, this integral goes to 0. And this entire term now goes away. And since I want this to equal 4, I then know that c needs to be 4 e to the minus 1/4. So I can then plug that in and get that my function y of t is going to be 1/2 e to the t squared over 4 integral from 1 to t of e to the minus s squared over 4 ds plus 4 e to the minus 1/4 e to the t squared over 4. And you could combine these if you want to, but you don't have to, as that works for an answer to this problem. The key point here is answers can involve integrals. You should try to avoid it when possible, but there are times when you will not be able to solve the integral and you have to leave the answer like that. And to do that and make it look nicer, you want to pick the initial condition value for t as the lower limit of this integral. So there's an example of how these work out even when you can't evaluate all the integrals in the problem.